Hello, everyone. I'm Wonchan Lee from NVIDIA, and today I want to talk about Legate, which is a programming framework that our team is working on. And even though I said Legate and cuPyNumeric, I'm not going to say much about cuPyNumeric, mostly Legate, so it's a lie. Um, okay, so the motivation is the productivity of the programmers. So there are many researchers and scientists who want to use the modern hardware for getting their science done faster. But the problem is that they're not programmers. They don't know how to write programs for these complex machines. So they end up just kind of sticking to the sequential like NumPy implementation or some Python implementation that take forever to do their science, right? So, and oftentimes these researchers end up working with some real computer scientists and programmers who know how to write programs. So the initial prototype is usually rewritten to something more serious like NPI, right? So there's basically a big productivity gap that we want to kind of address with the Legate project. And the high level idea is the zero code change scaling, which is a marketing term. So instead of asking them to be an expert programmer for all these complex hardware, we want the researchers and scientists to write their programs using familiar APIs like NumPy, SciPy, Pandas, and all the good stuff, right? So they write their programs mixing these libraries in the program. And then they still be able to run this program on any machines they want, right? So that's why we're saying zero code change scaling. So how do we actually do this, right? So there are quite a few libraries that people are using for their kind of daily programming, like NumPy and SciPy, of course. But if you kind of select the kind of foundational Python libraries, there will still be many things that we need to cover in this kind of mission. Right? So the high level idea is instead of tackling these libraries individually and making them scalable, we want to build a common foundation, common framework that will solve the common scaling problems in a more uniform way. So that's where this Legate framework comes in. So there are many problems people have to kind of solve when it comes to scalable computing, right? So data partitioning is one. So to use multiple GPUs, you have to partition data. And once you partition the data, you have to move the data around between different GPUs to maintain the coherence, right? And figuring out the right partitions especially for non-expert programmers, is challenging, right? And of course, we want the programs to run fast and scale in a scalable manner on all these machines, right? And on top of that, another kind of challenge that is kind of particular to this productive setting is that people often use multiple libraries in one program. So it's not sufficient for individual libraries to be scalable, but they also need to be scalable in a collective sense. So when they're using the same program, they should be scalable collectively, right? So that's where this composability and interoperability really becomes a problem. And by having a uniform framework that kind of standardizes the library implementation actually helps address the composability issue. So that's the high-level idea of Legate framework, right? And we've been working on this framework for the past 2 years, and we were able to write several libraries on top of this framework, including cuPyNumeric, which is a NumPy replacement built on top of Legate. And we have Legate Sparse, which Ron will be talking about in the next in the next session. And Legate Data Frame, Raft, Boots, these are all for data analytics, and also we have IO library. And of course, this is a Legion retreat. So we're building this stuff on top of Legion because Legion already solved almost all the problems that I just mentioned, right? So Legion has been pioneering the idea of scalable implicit parallelism for hardware, for software. And it comes with the first class support for data partitioning. So it knows how to deal with the data partitions and different partitions of the same data. And it also supports the coherence management. And we recently discovered that the right way to think about this partitioning problem might be constraint based. Instead of asking the user to write partitioning code directly, we just ask them to specify what the desirable partition should look like, and the framework should figure that out automatically based on the specification, right? So this is a high-level idea of Legate framework. So here's how Legate actually works. So a typical Legate program will make a sequence of API calls that may or may not be from different libraries, right? So you can have like Legate IO for IO and sorry, there's cuPyNumeric. cuPyNumeric for numerical computation and data frame for the data processing and all that stuff, right? And all these libraries will eventually produce something called scale-free tasks. Right? So the scale-free tasks are not describing how the computation should be parallelized across the machine, but instead it kind of gives a specification of what the desirable parallelization should be for this individual library operations, right? So as a library developer, you're only responsible for describing your computation and not actually doing the explicit data partitioning and also any data movement and synchronization between these tasks, right? So each of these libraries are kind of self-contained and do not really think about what other libraries would do, right? So this is by construction are kind of composable, and also this setting makes it a lot easier to make libraries transparently scalable, right? So I'll talk about what scale-free task really is in the next slide. And once libraries kind of submit all these scale-free tasks, the framework now take these tasks and convert them into actual parallel tasks that you can run on the hardware, right? So the first layer in the framework is like a core. It will be responsible for parallelizing all these scale-free tasks into scaled tasks, right? And once we have some number of tasks, we'll submit that to the Legion runtime, and the Legion will figure out the data dependencies between tasks, right? And finally, Realm will be responsible for running this test graph in a scalable manner on any machine that you pick, right? So this is how Legate works in a brief summary, right? So then what the scale-free task really looks like, what you should do as a programmer to kind of enjoy this benefit, right? So here is a code example that I brought, which is multi-GPU batch FFTs. So if you do FFT on only one of the dimensions, then that FFT can be easily parallelized by partitioning the other dimensions that we don't do FFTs in, right? So this is called batch FFT, and we can easily parallelize it on multiple GPUs, right? So the very first step to write multi-GPU batch FFT in Legate will be define the task, right? So task is nothing but just a Python function with some decorator saying that this is a task, right? And since the runtime needs to know how to kind of reason about the data dependencies with other tasks, the task needs to specify how the function will be using the data, or whether it's reading the data or writing to the data, right? So that's being specified and in the form of type annotations, right? So we cannot arbitrarily reason about any data usage of a function, but instead we want the function to be specific about how the data how we'll be using the data, right? So we offer the type annotations so that the task can describe how the data will be used for the function. And then inside the function, you can use any single processor Python library you want, right? So we implement all the usual array protocol, like for NumPy and cuPy, so that you can reuse existing single GPU libraries or single CPU libraries for filling in the task definition, right? So once you have this much of code, this will be just a normal Python function that you can use in any arbitrary context. And what we actually want to do is run this function on multiple GPUs, right? That's where the partitioning constraints come in, right? So there are certain type of partition that you can do for this function, right? And we want to be able to describe that without actually creating the partitions. So the partitioning constraint will kind of tell the framework that this is a desirable properties of the partition that need to be created for this function, right? So that's partitioning constraint at a high level. If I describe, since we're doing batch FFT, we don't want to partition the dimension that is being used for the FFT computation, right? So that's the two lines there is basically saying that, right? So once you have this much of the task definition, then you can just invoke it like a Python function, right? But behind the scene, what's happening is that the framework will take this function, partition the data, for all the GPUs and launch the tasks on all the GPUs, right? So it's deceptively simple. It's like a Python function, but it's actually being uh, parallelized for multi-GPU execution. And uh, another kind of benefit of this formulation is I kind of pass in some output from a cuPyNumeric call, which is another library that is independent of this function, right? So this kind of composability can be kind of nicely captured by this formulation, right? Without needing to think about how the data will be partitioned, right? Okay, so here, when I was kind of putting together the slide deck, I realized that I kind of sent out a plan in the last retreat, right? And this is kind of the recurring thing that we do in the Legion project, like to see how much we've accomplished uh, for things that we kind of planned and promised in the grand plan document, right? So I did that for the Legate project. And it looks like we hit the kind of perfect score, right? Because so we kind of know what's gonna happen in 2 years, right? So the first thing, beta release. So we had a big announcement at supercomputing this year. That's the reason why we have a new name for the library. So instead of cuNumeric, now it's cuPyNumeric. Okay? And the actual use cases from Quinn, and she's gonna talk more about her use case of cuPyNumeric. Okay. For FFT and linear algebra, we integrated all the good stuff from NVIDIA advanced libraries, cuFFT, cuSolver, and the multi-GPU version of it. So now we're hitting like 70% API coverage, and we can also support multi-GPU execution for non-trivial linear algebra routines and FFTs. And for IO function, we had a different idea. Instead of implementing the NumPy IO API directly, we added a new library because we can actually compose it, right? So now we have Legate IO for the IO library, and also Legate data frame, which kind of understand some of the well-known file formats like Parquet and CSVs and all those stuff, right? So by mixing these libraries with other Legate libraries, you can have the full story from IO all the way to the computation. And mapping heuristics. So honestly, we haven't made much progress on this front, but we did one API extension, which is user-provided hint for the instance bloating. So sometimes if you're doing stencil computation, it'd be useful to kind of prefetch the halo of your stencil, right? Instead of kind of incrementally discovering. So we added an API so the user can specify that you're actually doing stencil computation. This actually helps with the memory scaling for stencil like program patterns. And we completely rewrote the Legate core layer, which used to be written in Python, but now it's completely in C++. Automatic machine configuration. So if you are familiar with how Legion works, you have to specify the number of GPUs and size of the frame buffer and number of CPUs and all the stuff, the whole machine configuration. That might be useful and sometimes helpful for the Legion developers, but the users that we are addressing, they don't necessarily know how to configure the machine in the correct way. So we offered automatic machine configuration capability, so users don't need to specify these machine flags. The machine flags can be given, but those are optional now. And there's some peculiarity with the Python interpreter, with the GIL and other stuff. So we started as a kind of custom Python interpreter, and we use it for running Legate programs and cuPyNumeric programs. But now we made code changes so that you can use the Python interpreter instead of the custom launcher for running Legate programs. And finally, all the Kanda packages are now kind of capable of multi-node execution. So it is shipped with the network support, UCX and GASNet. So you can start running things on multiple GPUs and multiple nodes just by downloading our Kanda packages. So that's a great improvement in terms of usability. So from now on, I'm going to talk about individual updates that I think are important. The first one, again, the rewriting Legate core in C++, right? So Legate used to be a Python layer, so sometimes it's kind of difficult to use it in other languages. right? And also Python is really slow for doing anything serious. So we had to rewrite it to C++. And the porting actually is done in 2023, and all the libraries since then have been developed on top of a new Legate core implementation. And we do have Python binding, so most of these libraries still kind of use the same APIs as they used to with the old Python core. But some of the libraries decide to just go directly to C++. So for example, Legate data frame, which is our data frame implementation, that's built directly on top of Legate core C++, right? And the reason is that they want to be able to use this multi-GPU data frame library in other languages, especially in C++, and potentially in Rust and other languages too, right? So it kind of uses C++ API. It has its own Python binding. So that's kind of the pleasant surprise that some people decide to use C++ API instead. And another possibility that kind of popped up with the new C++ API and C++ implementation was Legate STL, right? So Eric Niebler, who's our C++ guru at NVIDIA, he decided to kind of use Legate for building STL-like functional algorithms library built on top of Legate, right? So here's a code snippet for Legate STL. So high level idea is that you kind of call some STL-like functions like fill and for each and transform reduce type of stuff to write your C++ programs. But this program will just automatically run on any number of GPUs, any number of CPUs for that matter, right? And in terms of implementation, Legate STL is kind of a thin template wrapper around the Legate core concept. So this was done in the time frame of 2 months, if I remember correctly. But again, this is a nice productivity feature that we were able to add because we have the C++ implementation and C++ API. And another big thing that has happened was Python task support. So the code example that I just showed you didn't exist 2 years ago. And now we have the full story for Python development, right? So one of the complaints with the Legate framework into 2022 and 2023 still is that people have to kind of do this hybrid programming where you use Python API for launching tasks, but for the actual task implementation, you have to use C++, right? Or you just go directly to C++ and build a Python binding for yourself, right? So that's not really Pythonic. So we decided to work on add support for Python tasks, right? So tasks can now be defined in Python with some decorators. And like I said previously, all these data containers implement the typical protocols so that you can use existing single processor libraries. And the side benefit of this task, Python task formulation is that it kind of eliminates all the boilerplate for describing the launch, right? So if you remember the slide from Elliot's presentation, you had the for loop and you have a function call for launching tasks. This one doesn't even have a for loop, right? It's just a function call, right? And behind the scene, it will be doing the parallelization automatically, right? And we can do that only because we specify, we kind of take all the necessary information in the form of type annotations and also the decorator arguments. Okay. So the next thing is Legate Rapids, right? Data analytics is a kind of big area in the Python community, especially the PyData and all the good libraries. So we cannot just ignore the existence of the data analytics. And fortunately, NVIDIA has been putting a lot of effort to support data analytics workloads, right? So that's called Rapids libraries. So we decided to combine the two, the Rapid libraries and the Legate, so that we can deliver more scalable data analytics and also ease of use. So this effort leads to the three libraries that I just mentioned, the data frame library and the three gradient boosting library, Legate Boost, and also the machine learning library. And we found the perfect benchmark that can use all these libraries in one setting, right? So there's the benchmark called Rapid GPU XD AI, which is mostly derived from the TPCX AI benchmark. And the high level idea is that this benchmark is modeling what typical data scientists would do. They would typically load the data, do some ETL with the data frame processing, and then eventually pass the data to training algorithm and eventually doing some model serving, right? So this use cases, there are 11 use cases, I think, all consist of uh, ETL, machine learning, and also data loading components, right? So we thought that this is a perfect use case, use case for really showcasing the composability claim that we've been making with the Legate framework, right? So in fact, we had to use 4 different libraries for implementing these use cases. And here's some preliminary performance results. And there are not many TPCX AI implementations that we can compare with, especially the GPU implementation. So what we did was we took the official record, TPCX AI record from the official website, and we also run our versions of GPU-XP AI, which are not quite TPCX AI, but it's similar enough, right? And we compare the performance between the two. And since all these official records are CPU based, so we cannot just directly compare the numbers between the two because it's apples to oranges. So what we did is we factored the cost of the hardware into account so that we can say the cost effectiveness of Legate libraries, right? So I don't want to read the table, the plots closely, but the high level idea is that we were able to confirm that using GPUs would be a lot more cost effective for this type of workload, especially for this scale. And we were able to find the same implementation, but written with Dask, and we were able to compare the performance on 16 GPUs. And one thing I should mention about Dask implementation is that this Dask implementation also uses all the Rapids libraries, right? All the kernels that we've been developing. So the only difference between the two at this point is just the runtime system, right? But even the runtime system alone can make the two like 1.4 to 2.5x difference, right? So I think this really highlighted the kind of importance of a scalable runtime system. So out of 3 Legate Rapid libraries, I want to call out the Legate Boost library because this has an interesting story, right? So Legate Boost actually was started as a research project within the company. So nobody asked for it. And Rory Mitchell, who's been a regular contributor to XGBoost, which is a very popular gradient boosting library, he one day showed up at the sync up and said, he's working on this boosting library. Nobody asked for it. And he was pleasantly surprised that he can just use cuPyNumeric for like 80–90% of his implementation. So within like a couple of months, he was able to build a library that is quite competitive with XGBoost in terms of capability. And he can even build something that's quite difficult to do in XGBoost, such as custom objective functions, right?
You don't need to share.
I thought I was sharing.
Turns out you don't.
Okay. Okay. Let me go back to that. Okay. Right. So if you think about supporting custom object functions in a library that is implemented in C++, right? So we're talking about like a whole lot of like plug-in interface so that people can write some custom blob of binary and plug it into the existing C++ framework. But in our case, we don't actually have to do that. Users just write cuPyNumeric functions and pass it to Legate Boost, and Legate Boost will just mix it with the custom tasks that it has, right? So this is a kind of comment from that Rory Mitchell made about Legate Boost, right? So he was really impressed that he was able to be more productive in actually making enhancement in the boosting algorithms and boosting library without needing to worry about all the technical details of C++ and MPI and all the internal communication data management. And like I said, the performance is quite competitive. So the first plot is quite hard to read, but that was about the training accuracy, and we compared it with XGBoost, and the training training performance is competitive with XGBoost in terms of the time to convergence, and on the bottom we have some scaling result and the performance comparison with XGBoost. So for some of them we're faster, some of them we're slower, but still. In terms of performance, it's kind of hard to kind of distinguish between the two. And of course, Legate Boost can scale to 1,000 GPUs from the beginning. So another thing that popped up, which is actually Rohan's research and not mine, I'm taking his credit, was the cross-library kernel fusion and task fusion. So because all these libraries are built on top of the same framework, we can actually merge the kernels from multiple libraries and kind of produce one kind of fast kernel out of these different library implementations. So here's one example with Legate Sparse and cuPyNumeric. And so the high-level idea is that Legate, instead of kind of eagerly executing all the tasks coming from libraries, we kind of batch them into a window and find a subset that can be fused into one task and one kernel, right? And for doing the kernel fusion, Rohan had to rewrite some of the tasks into MLIR-based representation, but still we were able to do the kernel fusion. And once the fusion is done, we kind of submit a fewer number of tasks to the runtime, right? So the benefit is the test launch over is smaller. In the process, we can identify temporal locations and we can eliminate them. And because we don't have temporal location that need to be passed between tasks, the data movement will be also removed, right? So here's some performance numbers, right? So the fuse execution can be quite competitive with the PETC, which is an MPI-based implementation, right? And I think this is the final slide before the conclusion, right? So lastly, the thing that we worked on is the profiling, right? So sometimes we are using LegionProf for profiling Legate programs, Legate application performance, but sometimes we have to use Insight systems for actually seeing kernel activities, right? So we thought that it would be good to have one kind of comprehensive view for everything. So this Insight system integration actually allows you kind of render all the Legate level and Legion level activities at the top, and still kind of have the physical views of the world, like the kernel activities and all the CPU operating system and network, all in the same profile, so that we can easily navigate between two different worlds, two different views of the same execution, right? And we kind of annotate all the tasks with the domain information about Legate libraries, so that you can actually identify where these operations are coming from, which library these belong, and things like that. So hopefully this will be kind of more useful for actually better understanding the performance issues with Legate programs. Okay. So all our packages are already available on Conda, so you can install it today and start hacking it. So Conda install cuPyNumeric will give you Legate and cuPyNumeric. And for any questions and comments, please contact us on that email address or the discussion page on GitHub. And here are some resources that you can kind of look into to learn more about Legate and cuPyNumeric. And that's it.